Hello, Chemistry 20. Welcome to week 3 of distant learning. I hope that you are all doing well. If you're listening to this, remember, if there's something else that you need that would support you, make sure to let me know, and I'll do my best to help you how I can. We are starting into a brand new unit today. So this one is about solutions, acids, and bases. Again, lots of number crunching, just like we were in the previous gas unit, and a lot of formulas and concepts that are so important for you guys to get down as we are leading eventually next year into chemistry 30. So keep that in the back of your heads that the concepts that we're doing, honestly, from right now until the end of June are really key for you to be clicking into as you approach. This is a prerequisite course for Chem 30. Okay, let's go into things. So our focus here today is going to be on types of solutions specifically. And some of this is going to be familiar to you, but the way we go about the equations is probably going to feel a little bit different. I'll show you what I mean. So first things first, this is review. Type of solution in general is consisting of two items, and you know what these are, solute and a solvent. And sometimes the idea of what a solute and a solvent gets kind of skewed when you're a little bit lower grades. Ultimately, if you're trying to define what a solvent is, it's simply whatever item in the solution there's the most of. So whatever there's the largest quantity of automatically gets solvent. And solvents can be solids, they can be liquids, they can be gases. It's not a defined entity. As you keep on going into a solute, this by definition is whatever is dissolved in the solvent. So naturally, there's going to be less proportionally of a solute than there is of a solvent. And I mean, if you look at this example right here, this is the most simplistic example that you've been seeing since you were a little kid. If you take some water and you've got more water than you do sugar, which you add in, the sugar dissolves. Of course, the water is going to be your solvent in this case because there's a much greater quantity of it. It's not a solvent because it's water. It's a solvent because there's more. Vice versa, the sugar, we have a lower amount, and that makes this the solute, which in the end, we have a simple solution. No big deal. We do focus on solutions where water is the solvent through the remainder of this course. But do be aware that, like I said, solvents can be many different things. It doesn't have to be water by any means. However, if it is water, then we have a scenario where it's aqueous, right? That's not a new word to you, but notice the root of this is aqua, which of course means water. So an aqueous solution is a solution where water is the solvent. That's key. And these are what we've been familiar with for years now. They're transparent, they may have a color, they may be completely clear. It varies depending upon the ions that are dissolved in there. But ultimately, a solution where water is the solvent. Okay, couple things that we still need to talk about before we go into 3 specific type of solutions. And that's these two concepts, an electrolyte versus a non-electrolyte. And notice the root of this word, electro. That's referring to, honestly, electricity. So the ability to actually conduct an electrical current or not. And the cool thing is, as soon as you dissolve something in water, if it does conduct current, then we have a scenario where it's an electrolyte. And there's 2 types that often form electrolytes. Ionic compounds dissolve to do this, and so will acids. So if you're someone who drinks Gatorade or Powerade or something like that, perhaps you're an athlete, then honestly, that's what you're doing. When you're drinking it and you're getting electrolytes from it, it just means there's dissolved salts, and salts are always ionic compounds. So little side note there. Keep going, and let's consider a non-electrolyte. This is super logical too. It does not conduct electricity, which honestly means, guys, that there are no ions present. If there's no ions present, then we're not going to be able to conduct. Now, the best example of a chemical substance where it does not conduct electricity are molecular compounds. So for example, let's say you do dissolve sugar in water. It's not going to conduct electricity. Okay? All right. Now that we got that clear, aqueous solution, electrolyte, non-electrolyte, let's start to go into the specific solutions that we'll focus in on. And here's a good comparison of two of them that we're going to look at. A on this side is sodium chloride. Now think about what sodium chloride is. Sodium is a metal ion. Chloride is a non-metal ion. So this is an ionic compound for sure. If it's an ionic compound, then we end up with ions that are dissolved. Those ions get split up by the water molecules. I don't know if you can see this, but the water molecules are these red and white ones, right? Those are water. And they surround the ions. They surround the sodium ion over here. They surround, that's the other one. That's the chloride ion. Right here, chloride ion. And they surround the sodium ions here. So they split them up. Hence, dissolving occurs. That's one scenario. Now look over here to this one. This is basic sugar, right? Sucrose. So when you have sugar that you put in tea or something like that, this is what you're eating. This is definitely a molecular compound. There's no ions present. It's all sharing of electrons. A little bit of a different scenario. In this case, we end up with our sucrose being crystallized and breaking into separate molecules, not ions, molecules. And then the water molecules surround those. Okay, two different scenarios for how dissolving can occur. Keep that in the back of your head as we keep on going. So speaking of molecular compounds as our focus, remember, keep that sugar in the back of your head. This is where individual molecules spread out. And again, I have to emphasize to you, we're not talking about ions here. It's all about the molecules. So when that molecular compound is dissolved in water, then we have that situation where the water molecules will surround the glucose molecules, the sugar molecules, okay? Or the sucrose, whatever type it is. Now, ultimately then, these individual molecules, and notice that they are neutral, so we've got no ions. That's key again, no charge, spread throughout the solution. Because they're spreading apart, that's dissolving. Key language. Do not lose sight of what this is called. Separation. Make sure that you know that word. Make sure that you relate it to molecular compounds and how they dissolve. I'll give you an example. Check this one out. If we take dissolving sugar, and specifically this is the chemical formula for a sugar called sucrose, we started out where the sucrose is solid. Right? And ultimately all that's happening then is we're going to add some water. And when water gets added, then we end up with no longer a solid sucrose, but, and this is important, take note of it, an aqueous solution. So please be aware of our different states of matter as dissolving happens with a molecular compound. Starts as a solid, add some water, ends up as an aqueous, and check out the language, solution. Okay? But be well aware, there are absolutely no ions present. It will not conduct electricity. Hence, I've got the electrical sign there crossed out. Okay? Will not conduct. Separation, molecular compounds. Let's check out going back then to that diagram. That means that this here on the right side is an example of separation. Okay, look at the next one. Dissociation. Alrighty, when we deal with dissociation, then we have a scenario where this is ionic compounds. Okay, now dissociation is when we have those crystal lattice shapes, and the crystal lattice shape of the ionic compounds splits, this is key, into individual ions. So if these ions spread through the solution, then we end up with a similar picture to what I showed you before, but where literally negative ions are surrounded with water, positive ions are surrounded with water, and as the water goes all the way around those ions, they split up. Hence the solid dissolves. Okay? Now remember, language-wise, dissociation. And without a doubt, as you look at this, ions are present. There is no question about this whatsoever. Again, go back. to this diagram, make sure that you note for yourself that diagram A is dissociation. That's key. A couple examples of dissociation is taking essentially any ionic compound, for example, table salt, sodium chloride. Notice it's going to start as a solid. We are going to add some water. And when we add water, this is going to split up into its separate ions. The positive sodium cation, the negative chloride anion. But do not lose sight of the states of matter. You must change them. In this case, from solid to aqueous, because it is dissolved in water. It is an aqueous solution. Example 2, check out this one, magnesium fluoride. Now, something to recognize is making correctly balanced ionic formulas is still super important. In this case, magnesium has a charge of 2 plus, and fluorine has a charge of 1 negative. So when we balance it, I've got 2 fluoride ions to every 1 magnesium. Check out over here, when this thing dissociates, splits into its ions, you still have to recognize the balancing, which means 2 fluoride ions have been produced. Do not lose sight of that. Keep in mind again that those ions are going to be aqueous as they change state from the original ionic compound in solid form. Do not lose sight of those. Okay. Take note as well, please, that they have to have their proper charges. If magnesium cation normally has a 2 plus charge, when it dissociates, that equation has to communicate that. All right, 2 scenarios so far. Separation of molecular compounds, dissociation of ionic compounds. Our next one here is... Oh, actually, let's talk about this one first really quick. Bases. Bases are still ionic compounds, guys. I do mention them specifically just because we'll refer to acids in a moment. But ultimately, don't lose sight that a base is an ionic compound. It has an ion called hydroxide, so that when it dissociates, it is those hydroxide ions that give us basic properties, right? Things like tasting bitter, feeling slippery on your hands, and the classic one that's probably most familiar to you, turning litmus paper blue. Whether it is red litmus paper turning blue or blue litmus paper remaining blue, same thing applies, okay? So as long as, in other words, you have an ionic compound, which this base is, then you know that it's going to undergo dissociation, right? So we take it in solid form, add some water, and when it dissolves, you will end up with an aqueous solution where it is split into its individual ions. Once again, make sure things are balanced. If I have 2 hydroxides going in, then 2 hydroxides are going out, from solid to aqueous. Ionic compounds, when they undergo dissociation, when they dissolve, there are, beyond a shadow of a doubt, ions present, which means for sure these are going to conduct electricity. Of course they will. Okay? So think about that. If ions are present, then conducting of electricity will occur. Okay, now we'll move on to the third one. Third one here involves acids. So going into acids means that we have an interesting situation where technically the acid starts as a molecular compound. Okay, so if it starts as a molecular compound, it doesn't have any ions, it's just neutral. But here's where things get interesting. When you dissolve an acid in water, then we have proven in the lab, there's no doubt about this, that electrolytes are present, which means they do conduct electricity. If they conduct electricity, that must mean that ions are present. How else would this occur? So think about how weird this is. They start neutral, no ions, and they end as electrolytes, which means, yes, ions. That's weird. That must mean that a process is occurring that is different than separation, different than simple dissociation, and we call this ionization. And ionization is actually a reaction, and a reaction where these neutral atoms become charged ions. They started neutral and they become charged, ionized, if you will. Give you an example. Take hydrogen chloride gas. So if we have this gas that gets bubbled into water, so again, we're going to add some water, then what was a molecular compound with two nonmetals will become ionized, will become ions. H plus aqueous, Cl negative aqueous. In other words, what began not aqueous turns into aqueous in the end. Make sure you make note of that again. We start as a gas and we finish aqueous. Okay? Since, without a doubt, ions are present, then they will conduct electricity. Little side note, guys, acids are not all created equally. They're definitely strong versus weak acids, and we'll talk way more about that as we continue on in this unit. Ultimately, strong acids are going to have more obvious acidic properties, whereas weak acids are not going to be as pronounced. Okay, let's summarize this to get to the end here. I've got 4 different types of solutes. So again, a solute is something that is going to be in smaller quantity compared to the solvent, which in this case is going to be water for all of them. Look at the first one. It's a molecular compound. And if you glance at this thing, this is not an acid. Yeah, there's hydrogen present, but we've got a strong molecular compound here of our glucose, right? C6H12O6. If this molecular compound is put into water, will it dissolve? Sure. Will it conduct electricity? Definitely not. Okay? Therefore, will it have an effect on red litmus paper? No, it's going to stay the same. Will it have an effect on blue litmus paper? No, it will stay the same because these are completely neutral atoms without having any hydrogen ion or any hydroxide ion. Check out the next one. An acid. This is called nitric acid. So if I take nitric acid, which in its pure form is a liquid, and I put it into water as a solvent, which means it will become aqueous, then it will undergo, it's an acid, ionization. Ions will later be present then, so yes, it will conduct electricity. If it is an acid, then it will turn red litmus paper, or remain, I guess, red litmus paper red, and it will make blue litmus paper turn red. Next one. A neutral ionic compound. And there's an example given you there, lithium chloride. So lithium chloride, when you put it in water, will dissociate into its individual ions, lithium plus and Cl negative, both aqueous. If ions are present, yes, it will conduct electricity. However, it is not acidic or basic. It has no hydrogen ions that were made. It has no hydroxide, so it will have no effect on red. Will have no effect on blue. Honestly, that means red will stay red, blue will stay blue, right? That's how that ultimately comes down to. Red stays red, blue stays blue. Red stays red for our glucose as well, blue stays blue. Same. Last one, an ionic compound that is a base. We know it's a base because of that hydroxide. That's the key entity that's there. It is still a type of an ionic compound, which means it will still conduct electricity because ions will be present. But it will turn red litmus paper blue and it will keep blue litmus paper blue. And there you have it, guys, a summary of our 3 different types of solutions. Dealing with separation of molecular compounds, dissociation of ionic compounds, which includes bases, and ionization of acids. You should go to your assignment now, and you have the ability at this point to complete number 1 and our new assignment 3. Talk to you soon. Take care, guys.